Okay, I think we can get started. So welcome everyone to this talk for the DEGA webinar series. So it's my pleasure today to introduce Alvin Issoufy. He did his master's and bachelor at the University of Perugia in Italy. And he did his PhD in 2019, actually here in our group in Delft. It was my pleasure to, was an honor to actually supervise Alvin. He was a great student. And for that PhD, he also got the IEEE SPS Best PhD Dissertation Award. So that was very nice. He also got many paper recognitions at different conferences. And right now, he's an assistant professor at the Computer Science Department of the TU Delft for our university. And he's also co-director of the Hydro Lab, which is an AI lab here at the university on water networks. And before his position here at the TU Delft, he was also a postdoc at the University of Pennsylvania. He's a member of the IEEE Signal Processing Society SPCOM Technical Committee, as well as the Youth Professional Committee. He's also associate editor of the Transactions on Signal Processing, and he used to be also editor for Elsevier Signal Processing. And last but not least, he's also co-organizer of the Graph Signal Processing Workshop, which will actually take place at the end of June here in Delft. So for those of you that are interested to come, so today is actually the last day that you can register for a cheap price. So have a look at the website and consider coming to Delft. So, okay, so that's it from my side. So go ahead, Alvin. Looking forward to your talk.
Yeah, thank you very much. Actually, it's a great pleasure to give a talk at the DEGA. Actually, I followed all possible talks, either in person, streamlined or online. And yeah, actually, I'm very, very honored to have Geert as my PhD advisor. And part of this work started at that time, and then is the path continuing nowadays. So let me see. Now, besides Geert, of course, which I'm extremely thankful, there are other people that contributed to this. Alejandro Ribeiro, Amanda Prorok already gave talks here, but also Fernando Gama, Mario Coutinho, and Zhang Gao. They also contributed a lot to what I'm going to present. And also, we have some funding agencies that made possible for us to do this research, which are listed here. Let's see. Now, we are at the DEGA talk, so I don't need to motivate much why graphs are important, but to set up the stage, we're going to consider the graph as a mathematical model for the data structure. This could be either a physical network, and then that's more easier there to motivate why we need the graph to represent the connectivity, but can also be like an abstract network, for instance, a functional connectivity in the brain. In those cases, we also have some data that are associated to the nodes, and this could be all sorts of recordings or activities thereof. In today's graph signal processing and graph machine learning paradigm, we want now to do solve some tasks that take into account the graph and the data. This could be as simple as a signal interpolation problem. So we have the data at some nodes and want to figure out the data at the other nodes. We want to classify these nodes based on the labels of their neighbors, predict links, or even forecast future values in times. Think of a road network. We want to predict the traffic in the future. And nowadays, as advertised many times here in DEGA, a lot of these techniques that are used are based on graph neural networks. They are quite powerful, and the interesting part there is that they try to learn a nonlinear mapping between in a training set that contains graphs and data of them, and they try to restrict the function space in a way that the graph is used as an inductive bias. And there is this paper here that I released from Peter Battaglia's group that tries to argue from inductive bias perspective. I recommend reading it. It's really interesting. And then, besides the fact that these are nice models for us to represent them, the success of GNNs has also been boosted a lot by industry. There are quite a few works that have shown real application of that in very quick time. I have here 3: estimated time of arrival at Google Maps, or recommending pins at Pinterest, or food at Uber Eats. But the more I see nowadays, I also realize LinkedIn is now based on graph neural network engine and so on. So they are really taking over in a lot of network-based applications. Now, because the graph is quite a versatile tool, there are different ways to capture information, and also GNNs came as after the success of neural networks in language and images. People start realizing, okay, I can build different way of architectures on how to aggregate the information between nodes, how to extract these patterns. That could be either following convolutional principle, attention principle, or other forms. This leaves, even nowadays, to a surge of architectures that we try to think, okay, what is the best way to extract this information? At the same time, becomes very difficult to principally compare them. So there are some numerical comparison, we see some marginal improvements in benchmark data sets, and then some of them go to other more challenging data sets to show if there will be more potential. But from understanding perspective, it becomes a bit difficult now in all this sea of architecture to figure out where to position each of them. And then the overarching question that I'm trying to answer in this talk is, can we, or how can we represent this GNN architecture, maybe with a unified framework, to highlight the advantages and the limitations of each of them. And I want to say upfront that there are a lot of the research here is done under the message passing framework. I'm going to propose an alternative to that that bridges a bit with graph signal processing. And this is the outline of the talk. So I'll discuss a bit the graph convolution neural networks. I'll then move to this edge varying perspective. And then I'll try to position the question before in terms of representational capacity and stability of GNNs. And I'll highlight a few future works. Now, GCNNs, to set up the terminology, we'll have a graph that is a tuple of a set of nodes V and a set of edges E. And we're going to represent the connectivity via a matrix S, which is sometimes referred to as the graph shift operator. You can think of that being the adjacency matrix of the graph, or the graph Laplacian, or normalizations thereof. And associated to this graph, we're also going to have a graph signal, which is a mapping from the node set to the set of real values. And we collect those values in this vector X, where each entry corresponds to a node. And this is shown here with these bars. Now, together, this operation leads to a very simple yet fundamental processing of signals. So if I multiply just S by X, I basically have a propagation of information to the one-hop neighbor. So very, very basic one. It's a localized operation that's going to be key to all the architectures in graph neural networks. Now, if we follow the shift and sum principle of convolution, I can take my signal X at the nodes, I multiply it with S, and I'm going to propagate it to one-hop neighbors. If I multiply it twice, I'm going to go to two-hop neighbors 3 times, and so on. So I'm shifting the signal over the graph. And if I multiply each of these shifts with a single scalar, what I'm building here is a shift and sum register, which is the principle of building a convolutional filter in standard signal processing. And in fact, this operation here is also coined as the graph convolution operation. And this is written in a form, is basically a summation of these powers. It's a polynomial in this matrix S with some parameters hk. And it's a local operation because every time nodes communicate with their neighbors. Now, that is a linear operation. So if I want to learn already with a filter, I can just learn the parameters there. I can design them. I can do a lot of things. But it's limited a bit to the linear space. If we want to learn nonlinear mappings, then we can follow the perceptron principle, where you basically take a filter, you put it inside a pointwise nonlinearity, and then you get the so-called graph perceptron. This graph perceptron now becomes the building block of graph neural networks, because basically you can just keep stacking them, or make them in parallel, and then you reach different type of architectures. And indeed, now I can define a loss function for my task and optimize that based on my parameters age of the filter. So we can see that in this perceptron, the graph is captured in the filter, and the pointwise nonlinearity just allows me to learn a nonlinear mapping to become a bit more expressive than the filter itself. And as I said before, we can build graph neural networks, convolution neural networks, by stacking layers. So I here have an input X, it goes to a filter, the output of that goes to pointwise nonlinearity, and this forms my first layer. The output of that layer goes to another filter, another pointwise nonlinearity, this becomes the second layer, and so on and so forth. And the propagation rule basically is indeed filtering with some polynomial of order k what comes from previous layer, and I can repeat this many times. And the output of these layers is going to be the output of my graph neural network, which is sort of an embedding that I can use for downstream tasks via readout layer. And indeed, in all this architecture, the graph is captured only in the different filters that are used in the layers. And if I change the filter here, so instead of using this polynomial, I'm going to use attention sort of filter, I'm going to have the graph attention network. If I use another type of orthogonal polynomial, I'm going to have the respective architecture. So Chebyshev polynomials is going to lead to ChebNet, Jacobi polynomials to JacobiNet, BERNet polynomials to BERNet, and so on and so forth. And by analyzing the filter, a lot of research has been extrapolated now to analyze, to obtain some insight on the GNN. But if we see it from a node perspective, these convolutional filters have this parameter sharing, which means that every node in the graph, when they collect the information from their neighbors, they're going to use the same parameter to weight them. So the blue node, regardless of from where the information is coming from, is going to use the same parameter age, which is also the same parameter used by the red node here, node 7, applied to all its neighbors. Now, this has some advantages. It keeps limited the number of parameters, is built on the convolution principle, and allows also permutation equivariance, so I can transfer this filter in other graphs. However, it has some limitations because I now have just I'm weighting in the same way the information of different neighbors, and I'm affecting somehow the expressive power. And we know either from distributed optimization or from, let's say, the attention perspective, that you want some discriminability in the information coming from your neighbors to allow to weight them differently. And that brings to the edge-varying graph neural network, which started as an idea to build filters, and then I moved it to the graph neural network. The basic principle is very simple, is to go the opposite way. So instead of sharing the parameters among all the nodes and weighting equally all the information of the neighbors, you do the opposite. You don't share nothing, you weight any information differently, and then those would be your parameters to design. So node 2 here is using a different parameter phi to 1 to weight information from node 1, and node 7 is using a different parameter for all their neighbors. So 578, 575, and so on and so forth. If I write this in terms with equations, it's very easy, becomes now a summation where I still propagate my signal via the shift operator in the same way. So I preserve this localized implementation, but then that shift, I'm going to weight it with different filter parameters. So this matrix phi k here is going to share the support with the shift operator plus the diagonal to allow maybe also reweighting your own shifted signal. And this was indeed some work done time ago with Mario Coutinho and Geert here. And indeed, once you have that, you can allow all the nodes, right, to build this filter. And the goal now becomes to design this this matrix K or to learn matrix phi K or to learn them. If now we want to build graph neural network and follow this perceptron principle, where I can do nothing more than just substitute the convolution filter with an edge-varying filter. And then I have now this set age that contains all the matrices phi that I need to design, where the number of the degrees of freedom now is much higher, and it depends on the sparsity of the graph. And I want to discuss a bit later that might be both a good thing or a limitation. So indeed, I have more flexibility. I might need now actually less depth because I have more degrees of freedom already in my filter to capture information. And I also need less filters in parallel compared to the convolution solution. The complexity remains linear in the number of edges m. The filter order k is quadratic in features, so filter banks, how many filters I put in parallel, and layer L, and also the parameters depend on that. Now, sometimes I may have a lot more parameters. So if I don't have enough training data, this might be a problem. In that case, we need to really penalize the degrees of freedom to reduce the function space and to reduce the degrees of freedom to learn meaningful mapping. Now, we tried time ago to use this filter for distributed consensus, and this is shown in the figure here on the left. So on the x-axis, we have the filter order, and we try with the filter to approximate the consensus operation, which is 1 transport over n. In some synthetic case, we can see with the red one is the graph convolution filter, with the blue one is this edge-varying filter that I just proposed, and the green one is an intermediate solution. And we can see that allowing these more degrees of freedom allowed us to actually approximate this finite time consensus, let's say, in less steps. So let's see, 5 iterations. And if we would use like a gossip algorithm, this might need more iteration to reach the same accuracy. Then Mario and Geert took this a step further, and they said, well, instead of using one filter, let me cascade these filters in parallel without nonlinearities, and that's what this cascade solution does. And you can see that in 30-something iterations, they were able to reach machine precision. And that's showing that this cascade starts to play a bigger role to approximate this. So I see there are a few questions in the chat. So there is a question saying if I have different graphs in different layers, actually the graph is the same. It's just that the filter can be learned differently in the different layers. And can the matrix phi deem a multiplicative perturbation to the GSOS? I see it as a parameter matrix right now, so maybe we'll come to this later on. Now, if we use this now with nonlinearities, we showed in this paper here in a couple of applications. One is the source localization, and the other one is the authorship attribution. And we can see here this edge variant achieves a very good mean performance compared to the convolution one or to some other solutions. And the same on this classifying authors. The other thing here to be highlighted is that statistically, this might perform more or less the same because the standard deviations are very high. And we realized that that is because there are outliers in the data set. So I didn't want to remove the outliers to get a smaller standard deviation. But what this shows is that it has the potential to achieve a very, very good performance for that. And now, sometimes you need to go to some hybrid solutions, so not allow full parameter sharing, but maybe select a few important nodes where to share. And that would improve the performance if you have fewer data. Other people also took this idea to develop other solutions. So there is this work here on the left, here on the bottom here, by Xian Chen and co-authors, that they built an unrolling, a model-based neural network for graphs to reconstruct signals. And inside their layers, they use this edge variant filter, which is sort of unrolled edge variant neural network, if you want to see that way. And they show in these 2 bottom rows that it actually leads to an improved performance. And this other work here by Zhang and co-authors, they show that if you use this to do forecasting, these increased degrees of freedom allow you to achieve a better performance in the forecasting compared to solutions that maybe use just convolution or other alternatives. Now, my point now remains that this EdgeNet is a general framework. It allows to assign different weights, and we need to impose, if we impose different restrictions on the parameters, we can achieve different architectures within it. For instance, if I force my edge weight parameters to share the attention principle, so instead of learning a pure edge weight, pure parameter, but I learn them via an attention principle, I can reduce them and still discriminate between the nodes, and that's what the graph attention network does. Instead, if I allow just a few of the nodes to share the parameters, which typically are isomorphic in the structure to each other, and then the other of nodes use a convolution sort of parameter, then I achieve a hybrid solution, and that's what this natural graph convolution paper from Maxwellian group does. And I can also extend this now to multi-hop attentions, which is something that we did in the paper before. So the point is that on the one hand, we have the convolution principle that shares parameters among all the nodes. And I'm trying to say on the other hand, you have this edge varying sort of perspective. And in between, now you can start placing all the intermediate solutions depending on the task or on which important nodes you have to capture information. And this intermediate solution now depends a bit to see how the different architectures limit the parameter space to explain how they propagate or aggregate the information between the neighbors. More recently, with Zhang Gao and Amanda Prorok, we start wondering, is any way now I can taxonomize this graph neural network differently and to start then seeing if I can say something beyond the parameter space of them. And we took the idea of stability to them. So the stability means if I learn on some graph G and I deploy in a perturbed version of them, how much will my performance deteriorate? And how can I now say something about the different architectures? And we came with this sort of taxonomization. We have here in blue the so-called architecture that are shift invariant. I'm going to discuss them. In green, some other architectures that are edge sharing invariant, and then the more general ones. So the shift invariant architectures are those where this filter matrix that you will learn commutes with a shift operator. And this implies that the parameters of your edge varying filter, so that its eigenvectors, are going to coincide with those of the shift operator S. So they need to live in the same, they need to have the same eigenvectors. And the graph convolution neural network is one case of those because it has this matrix phi is just a scalar identity. And that is a very particular case of these shift invariant solutions. And it allows, because I'm sharing this parameter, these eigenvectors, allows me to train on a particular graph and then go and test on other graphs. So this allows this transferability. However, as I said before, this will restrict my parameter space, and it's going to have some consequences also when I'm going to go to other slightly perturbed graphs. And there are other solutions, as I said before, that belong to this shift invariant category. Then if I move to the eigenvector sharing, what the eigenvector sharing category does, it says that my parameters matrix phi will have the same eigenvectors among them, but they can be different from those of the graph. So I'm imposing only the same eigenvectors among the learned parameters, the learned phis, but not with those of the graph. So I'm allowing a bit more flexibility compared to the topology. And the node varying graph neural network is a popular solution here. So what node varying does is that this matrix phi here is a diagonal matrix. And then that allows to have like identity matrix as the eigenvectors. So this node varying allows every node to use different weights, but they use the same weight in all their neighbors. And the attention network or this natural graph convolution are other categories that belong to this eigenvector sharing perspective. And then the question is, so what does this implicate? So what does this imply in terms of stability? So if I go from sharing the eigenvectors with the graph to not sharing them with the graph, but with the matrices, so what would be the implications of that? And that's what we try to analyze to some extent theoretically and then corroborate them with results. And this brings me to the other part of the talk. So I'm going to take a spectral perspective. So for that, I'm going to assume my shift operator has an eigendecomposition, right? Eigenvectors V, diagonal matrix of eigenvalues lambda, and other eigenvectors minus 1. Now, this is used a lot in graph signal processing because if this shift operator is Laplacian, I can sort the eigenvalues. And this allows me to measure the variability of these eigenvectors. There have been some talks here already to discuss all the GSP perspective of that. So I can now start sorting the different eigenvectors based on how they change over the graph. So I can take the eigenvector V1, plot it, let's say, over my nodes and consider that every entry belongs to a node. And then its variability is going to be the eigenvector lambda 1. If I go to the other eigenvector corresponding to the eigenvalue lambda 4, right, I'm going to see a bit more variability among the nodes. And the more I increase this, the most this variability increase. So this was maybe 1 decade ago, the turning point in graph signal processing to do this Fourier sort of analysis. So now I can take my eigenvectors. This could be also Hermitian or inverse. So here for Laplacian is Hermitian. So I can take my graph signal X, and then I can transform them into this eigenspace, so to the shift operator. And then I take this, then this X hat becomes the so-called graph Fourier transform. So now I can plot them with respect to the different eigenvalues. And this plot already shows me what type of variability my signal has on the graph or how much each of the eigenvectors contributes to the variability of the signal. And each of these coefficients now is going to measure the contribution of the respective eigenvector. This is analogous to the complex exponentials that are in time, where the Fourier transform coefficient is going to tell me how much each of the complex exponential with particular frequency contributes to the variability of the signal. Taking this eigendecomposition, and applying it to the filter, I can then get the Fourier transform of the filter output. That is diagonal matrix. This H applied to the eigenvalues lambda is a polynomial, this matrix lambda, and the Fourier transform of the input. So this is the expression of H here. So it's a polynomial in this diagonal matrix, which means that in each diagonal, main diagonal, in each entry, I'm going to have a polynomial applied to the respective eigenvalue. Then, if I learn these filter parameters HK, then I'm going to have learn them for a specific graph, and then I'm going to deploy them maybe to another graph. So let's see how it operates. So if I have this HK, the parameter fixed, what I'm learning is a polynomial in some analytic variable, in some variable lambda that I sort of plotted here. But when I learn them from data, I'm going to learn them on a particular graph. Let's say this red graph here. So I'm trying to learn this black shape or from samples in these red dots. When I go and deploy it, or I have a perturbed graph, I'm going to go and deploy it on the blue one. So I learn the black shape here, and then I go and deploy it on the blue one. That means that if the two graphs are very far away, or if I don't have a lot of data to populate this this line, then I'm going to have that this transferability going to pay a price. So I'm going to deteriorate in performance. This has been a relevant study for graph filters, graph neural networks, and so on. And one of the main ideas that was this pioneering work by Fernando Gama, João Bruno, and Leandro Ribeiro is to consider this perturbation to be small, to be like I preserve my my edge weight. There is some relative small perturbation about that, which is written here. So basically, this matrix E is small norm, and it's just perturbing a bit the weights of the graph. And that allows me to characterize the impact of the filter. So what they showed is if the filter frequency response, this black line, tends to be flat, so on the higher eigenvalues, which means that it's integral Lipschitz, in that case, we'll have that the filter and the graph convolutional network will be stable. And this is what this equation here says for the filter, is that if I train my filter on the blue graph, and I deploy on the red one, then the difference of the two output of filters is bounded by this term here, where we see the square root of number of nodes and this Lipschitz constant C, also the variability of the filter that I learned. And the same for the GCNN, you can extend this result to the graph convolutional neural networks. In that case, we see that this bound, this stability depends on the number of layers and depends on number of features powered in our number of layers. This means that while on one hand, we want to increase the depth of the GNNs and the width, so more filters and more layers. On the other hand, if I have a small perturbation, all this is going to amplify it and the performance is going to be worse. So I now start going towards the trade-off between either being more discriminative or being more stable. So what I showed so far is results that exist in literature about the stability of graph convolutional neural networks that are one point in this blue space here. And the question that we were wondering is, does the stability hold only for those type of filters, or can it also hold for other more expressive filters? And I'm going to analyze the filters that are with all the filters within this blue ellipsoid, so the shift invariant ones. So recall the shift invariant filters, the parameter matrix will share the eigenvectors with a shift operator. And in those cases, if I do the substitutions, I'm going to have that the output yi of my filter for a particular index I is going to depend on the eigenvalues phi I, that are the eigenvalues of my matrix phi, of my parameter matrix, and the eigenvalues of the graph lambda. So what I have now is, instead of having one single frequency response, when I go to learn edge variant matrix, instead of a scalar, I'm going to have n frequency responses when the parameters are shared. And this is shown in the plot here. So I'm going to have n different lines, and each of these lines, each of these responses is evaluated at a particular eigenvalue. So I can have the black line here is evaluated at lambda 1 for the red graph, and then when I deploy it and go to the green one, is going to be evaluated at the green lambda 1, the blue one, and so on and so forth. So each of them is evaluated at a particular one. So this shows a bit the flexibility when you learn more parameter matrices, more parameters between the different neighbors to go to the spectrum domain. Then what we proved is that if you allow or if you force each of these frequency responses to be integral Lifshitz, as it was for the simple one in the convolution case, it's easy to prove actually that these shift invariant categories, all the filters within that category, are stable. What does this imply? This implies that now I don't need to have a single integral Lifshitz because I don't have only one frequency response, but I can have a lot of them. So I can allow a bit more flexibility. So for the purple one that is evaluated at the higher frequencies, I can force it to be more flat, but instead for the blue one and the black one, I can allow them to be way more variable because the perturbation there is going to be smaller. Now, I think I said all of this. I can move on. And indeed, what we also have, what we have shown also is that if I reduce parameter matrices to be scaled identity, then what I will have is the result that goes back to the graph convolution neural network. So what we have here is a result that improves or generalizes a bit what already has been proven for the convolutional case. And then the question can be repeated again. So now I showed that this blue ellipsoid here, they are stable, the architecture there. Can I extend it to the green ones, right? And then brings me to this edge sharing. And if I extend, what are the trade-offs now what are the assumptions I need there? This eigenvector sharing will have that the matrices phi, again, will share the eigenvectors among them. So the parameters have the same eigenvector, the parameter matrices, but they can be different from the eigenvectors of the graph. So I have a bit more flexibility. So what we propose is to use what is called the eigenvector misalignment. So I try to see how the eigenvector matrices of the graph and the learned one are misaligned with each other. And we assume that they are not that much misaligned to prove the results. We assume there is some misalignment to some degree. Under that assumption, and for the filters to be integral Lifshitz, we can prove that also this category of shift invariant are stable. And in addition to the result we had before, we see here this term n times epsilon. This curvy epsilon is the misalignment between the two eigenvector matrices, and is multiplied by the number of nodes. So what we have is that even a small misalignment between these two eigenvectors is going to amplify the stability. So these are stable, but the stability bound is looser than what it was for the shift invariant one, and that because of this misalignment. So the error propagates in the graph is going to be amplified by the misalignment in the eigenvectors. And the smaller this misalignment, right, the more stable is going to be the architecture. And I'm now going towards this trade-off, right? So I went from the convolution architecture, the shift invariant ones that had more restriction on the parameter space. I went to the eigenvector sharing ones that have less restriction on the parameter space, but because of this freedom in the parameter space, I'm creating a misalignment in eigenvectors that is going to affect my stability. So if I increase the parameter space in that perspective, I'm going to pay in terms of stability if the graph is perturbed. And indeed, we also have a result in the paper, but can also be seen here that if the two eigenvectors get aligned perfectly with each other, so if the eigenvectors start coinciding, then the result here of the eigenvector sharing solution is going to coincide with that of the shift invariant architectures. Then finally, we were wondering if I can go to the more complete case, to the full edge-variant case, where I don't impose nothing on my parameters phi. In that case, each of these parameters can have their own eigenspace, their own eigenvectors, and each of them is going to be misaligned differently with the eigenvectors of the graph. So they are not even aligned among themselves. And in that case, under stricter integral Lifshitz conditions that I'm going to explain in a while, we can prove that indeed the same result can be achieved. The misalignment epsilon here, which is the maximum misalignment among all the pairs parameter in the graph, plays a role. What does this stronger condition mean? It means that since every eigenvector of the parameter matrix phi is misaligned with the graph, I have k of them. I can think of k different misalignments, And that allowed me to now think of this input-output relation of this filter as a k-dimensional shape. And so that becomes now, if we termed it as a k-dimensional filter frequency response, but this becomes now, instead of a line that I need to impose integral Lifshitz because I have k different misalignments, becomes like a hyperplane in this k-dimensional space. And I need to impose that each of these frequency responses that are multidimensional to be flat in all possible directions. So it's a much stronger assumption now to prove the stability. So bottom line, there are some sufficient conditions that to restrict this parameter matrices, not to allow for a lot of variability, that one can show that this more general edge-varying solution is also stable. And then this allowed me, so all these discussions so far allowed me to now start thinking of the different architectures in two perspectives. On the one hand, I have the representational capacity. So I have the convolution architectures that share parameters. So I'm using the parameters as a proxy of the degrees of freedom. And if it's low, I'm sharing more parameters, and the general solutions, the edge-varying one, do not share them. On the other hand, I have the stability perspective that if it is low, it means that I need stronger conditions to prove it, so more integral Lifshitz properties. I will have looser bounds and maybe also misalignments between the eigenvectors of the matrices. And I could populate now this plot very qualitatively here, where very stable solutions, but with lower parameter space, are the graph convolution neural networks. Then I can go to the shift invariant one. Then if I go allow the eigenvectors to be the same among the parameter matrices, then I'm going to this eigenvector sharing solution, which start paying a bit stability, but they have more expressivity. And if I go to the general solution of the edge-varying graph neural networks, I allow every node to weight differently the different neighbors. But in that case, I need way stronger conditions to prove stability, and the bound tend also to be looser. So all this is to say that there is a trade-off between representational capacity and stability. And in turn, this is going to depend on the number of filters F and depth L. Now, I want to make a remark here that what I showed so far is for the filter. If we extend it to a GNN, we can use result already exists, and it extends. But in that case, for the graph convolution neural network to be more expressive, you need more filters and more layers, which in turn is less stable. Instead, for the edge-varying case, because you have more degrees of freedom on the parameter matrices, you might need less filter in parallel in your filter bank and less layer. And in that case, the filter might be less stable, but as an architecture, it might tend to offer a better stability, let's say, that using a very deep GCNN. So there is this trade-off that is a bit needs to be quantified better in future works as well. The message here is indeed that simpler GNNs might achieve a better trade-off in some applications, but when they don't, you might want to go beyond them to allow more flexibility in your parameter space. And here are some results to corroborate this. So these are 3 experiments. One is source localization. In this case, we have some data that is diffused over the nodes based on different communities. And by observing that, we want to find out which of the communities generated the signal. The second one is a movie recommendation in a user-user collaborative filter using GNNs. And this is the authorship attribution, which basically a word adjacency network for each author is being built using functional words of the and etc. as nodes. They are connected based on some signature of the author, and we want to classify basically graphs and signals thereof. So what we see here is in blue, so this is performance versus perturbation. In blue is the shift invariance, so those that share more parameters with the nodes. In green are the eigenvector sharing, that intermediate solution. And in red is the solution with more degrees of freedom. So we can see here that if I don't have any perturbation, I can allow my edge-varying solution to really perform well. But as soon as I have some perturbation, I can see that when I share the parameters, it starts to get more stable. Instead, for the other, the eigenvector sharing or the full one, I can see that the performance degrades, and we see also the deviation also is affected. And the same result is also seen in these other data sets, maybe more visible here. So this is again accuracy, and we see that the accuracy of the shift invariant solution tend to be more stable compared to the other solution. And the last two plots. So here on the left, I'm plotting each dot is an architecture for different parameters, layers, features, order of the filter, etc. And I'm plotting the performance of them. In blue one is the convolutional one, and I can see that these are plots for a very small perturbation performance. As I start increasing the degrees of freedom, I can increase my accuracy, so I increase the depth, the width of the architecture. After a certain point, performance drops because the perturbation error gets amplified and propagated in more layers and filter banks. And likewise for the other architectures, they start with more parameters. And if I increase the number of features and the number of layers, I can see that it increased up to some point, but then it degrades as well. On the right plot here, we show in solid lines the empirical performance in the result, and in this transparent line, the bounds. And the message here is because these are all norm bounds, they respect, let's say, the shape, the trend in this the trend when the perturbation increases, but they might tend to be loose sometimes, especially if I have more and more layers, these bounds tend to be loose. But the important thing is that they tell us something about the trend of the performance when the perturbation increases, and that they are finite. So this architecture are stable. Now, to wrap up the talk, what I try to convey is that we can look at graph convolution neural network from a parameter perspective when nodes share the parameters or not among them. And then we could also taxonomize them based on how these parameter matrices are going to share the eigenvectors with the graph or among themselves. And then we can start populating all this space of architectures and to see which one could be in which category and how can I use them. Then I use this one to discuss the stability of these architectures. And what we showed is that the stability holds for all the architectures in the edge variant case, but we need stronger assumptions. So this is this one. So we have more assumptions. That's why I put it as low stability. And the more I restrict the parameter space, the less assumptions I need to prove the stability. Now, all this analysis, right, holds for sufficient conditions of stability. So one of the future works, I think that is very relevant, not only for what I presented, but for stability of neural networks, is to find necessary conditions, or even stronger one, necessary and sufficient conditions when these architectures are stable, and also to go to other type of perturbation models, which are very common. So we here have only relative perturbations, but we can think of nodes that being removed, edge that being added or dropped, and all sorts of them. So it's a bit more difficult to characterize them. And finally, I used the degrees of freedom of the architecture as a proxy for their representational capacity. But can we use maybe approximation theory of this architecture and then start discussing in terms of how the approximation theory, so how well they approximate a certain function and how that is related to stability. So these are three works that we are sort of looking right now. And as Geert said, we are organizing the GSP workshop in June. This is becoming a trend for me. I'm advertising it everywhere. So there'll be a lot of works, actually, also plenaries about graph neural networks, and you are all welcome to attend. Thank you very much.
Thanks, Alvin, for the very nice talk. So let's first maybe take some questions from the chat. So there was, still this question about whether the phi matrix is actually like a multiplicative perturbation on the shift operator.
So,
but yeah, it's not an element-wise product, right? So
no. So you can think of this phi matrix sharing the support with S. So you can think of it as a parametric shift operator. And this S to the power of kx is like a shifted signal, k time, and I'm shifting it once more, if you want to think it that way. But it's not is not a perturbation.
So then there's another question by Amir. So yeah, Amir, you can also unmute yourself if you want to ask the question live to Elvin. So it's about this wireless resource allocation. So suppose you would see this as a communication network and you try to learn the transmit power. So how can then the phi matrix be interpreted?
So the phi matrix in that case can be interpreted as how much weight are you going to put in every time when you exchange information between every transmitter and receiver. How that translates now to power allocation, I think is not that trivial, but can be seen as that link seems to be more important. And if you put some sparsity on this phi, you can actually learn where the few links that you might need to put more importance to solve a task, for instance.
Okay. Then another question was on slide 44. So there were two questions about that. So whether the misalignment is then the same for all the eigenvectors. So or is it for the matrix? So how is the misalignment between U and V? Is that per vector or?
Exactly. So we take every possible pair and try to see how much they are misaligned, and we take the maximum of them.
The maximum, okay. And then so there's the question. It seems that the stability bound doesn't go to 0 when epsilon goes to 0.
We can see it here. So if the misalignment is non-zero, I get the stability bound of the convolution architecture, which is the one here. And this convolution architecture depends on this epsilon, so maybe I'm missing that there, which is the perturbation between them. And then in that case, the two filters become the same. So I might miss this other non-curly epsilon later on.
So you mean there was actually like an epsilon in that bound in the
so the notation maybe needs to be changed for the future, but this epsilon is the perturbation in the graph. And I think here I need also the other epsilon.
I see.
The other one. My bad.
Got it.
Yeah. There was a question also about for a stable GNN, how many layers are required?
So to prove it, the result is shown here. It's a known result from Fernando and co-authors. So we use
the less the better, I guess, right? Yeah.
Exactly right. So we have here L is the number of layer, F is the features, and then this depends F to the power of L. So the less layer, the more stable. On the other hand, the less layer, the less discriminative the architecture is. So you are now playing a bit with them. So it's a trade-off now inherent.
And then the last question on the chat. Second last. So is there an information on the effect of the increased flexibility versus the number of on the number of parameters and then versus the network training time? Because now you have the trade-off with flexibility and stability, I guess, right? But what about the training time?
I think this edge-variant ones will take a bit more time to train, but that becomes also a way how you code them at some point. But for sure, the simpler the parameters that you learn, the easier it's going to be. So that depends. The real challenge there is that if you allow all the nodes to learn any parameter, you're going to have so many parameters as the number of edges. And if your graph is very dense, you need now to restrict that parameter space to add penalties on that as much as you can. And that's going to affect, right? If we penalize with, let's say, norm 1 on this vectorized matrix, it's going to affect the training time, of course. That's going to get slower.
Okay. Then another question about the simulation results. So it seems like smoothly labeled data sets, like the authorship data set, favors low capacity GNNs and vice versa. Does this have any theoretical or empirical support? So I guess that's your plot. That's your performance slide.
That is here.
Yes. Yeah.
right, in the auto-show attribution. I cannot say it for guarantee, but I think I've seen it also elsewhere, empirically at least, that if the data set is has a smooth label, so it's easier to maybe classify among the different data points, you might not need all that capacity to solve it, right? So that might be an indication, but I don't know any results right now about it.
Or is this also, could this also be related to the amount of training data that you have, that the less parameters here, you get a better result?
Yeah, for sure. So if you have a very limited training set, you need to take a lighter solution in that space in that aspect to train. Yeah, that's for sure.
Okay, thanks. Any other questions from the attendees? So just unmute yourself if you want to ask a question.
So I'm going to leave my slide with the GSP workshop. That's that's my target.
So if not, go ahead.
Do we get a copy of the slide?
I think it was about if we can share the slide. Yes, I'm gonna modify the typo there, add the other epsilon, and then share it to here, and then I guess.
Yeah, we will put it on the website of the DIGA, as I mentioned in the chat.
Thank you.
Any other questions for Alvin?
There's a new one. Yeah, there's a new one on the chat.
Okay.
For any neural networks with imbalance in data, accuracy is not the only metric. What happens in the GCNNs? Likely is going to be affected the same, but I didn't investigate that. That becomes now more data or data set perspective. So it's another, maybe needs other ways to analyze them.
Yes.
Yeah, maybe I have a final one. So actually also going back to the second results on slide 44 again. So do you have any way to interpret this sort of misalignment of eigenvectors? Like what kind of interpretation can we actually get from here? Like what kind of phi are we actually imposing here?
Yeah, so
if you,
the intuition I built around this is that if I'm training on the red graph S, right, my matrix is phi, and then they are slightly misaligned, let's say. When I go and deploy it on the blue one, they're still done, then it's going to be with some perturbation, and that perturbation might be amplified or it will be propagated by the misalignments. And that the more this misaligned, the more it propagates.
Right. I mean, my question is more like, what kind of weight matrices are we actually building?
Yeah, so now you need all a sort of regularization or constraint in your training to make these matrices to have this misalignment as small as possible, right? You need to do a constraint learning.
Yeah, right.
But yeah, this is more to give some insight. So it's the first idea on how to do that. So what we did right now is that we said, okay, I'm going to assume that all my parameter matrices share the eigenvectors, and I'm going to just parameterize their eigenvalues and learn there. So we just assume
that's what I understood. Yeah.
But if you let it wild to learn whatever, you might learn completely misaligned ones, and those might be also then lead to very bad stability performance.
I see. And also, like, what kind of what would be the U that you what kind of eigenvectors who gave us that eigenvectors U for the training of phi?
Yeah, we don't know how to fix that, right? That's the other. But the easier, that's
I see.
The easier solution here is to take order one filter, and then that can be anything. That's the idea.
I see. Yeah, thanks.
In my view, it opens a bit of a direction now that you know that you're going to pay in this misalignment, and now it's all other question how to train to be more stable, etc. There remains a lot of things remain unanswered still.
Yeah, right. Sure. Yeah, thanks.
Okay, if there are no more questions, then I think we can wrap it up here. So thanks again, Alvin, and thank you all for attending, and we will see you probably next month again for a new talk. So
Okay, thank you very
I don't
much.
for the next Degas talk.
Yeah, I see
Or
Stefan
yeah,
here. Hi,
yes.
Paulo. Hi.
Okay.
Right.
Hi, Alvin.